Hello, and welcome to Richardson RFPD's Tech Chat. I'm Kirk Barton, Field Application Engineer for Richardson RFPD, and I'm here today talking with Guy Moxey, Senior Director of Marketing for Wolfspeed. Thanks for joining the Tech Chat today, Guy.
Thanks, Kirk. Pleasure to be here.
And we'll be discussing gate drive voltage levels for Wolfspeed silicon carbide MOSFETs. So, Guy, a question I get asked frequently revolves around gate drive levels for silicon carbide. What is the gate drive requirement for Wolfspeed Gen3 MOSFETs?
It's also a question we get asked frequently too, Kurt. So let's get stuck into this. So first things first, look at the data sheet of any silicon carbide MOSFET, Wolfspeed MOSFET or anyone else's, because the data sheet will clearly say what the gate drive operational and maximum limits are. This slide here shows our generation 3 MOSFETs, which has a 15 volt positive continuous gate drive and a -4 negative continuous. But on top of that, because we realize there is noise and ringing, we allow up to a 19 volt transient positive and down to a -8 volt transient for negative.
Good. Good. So why is the negative voltage required, and is this always the case?
No, it's not actually. It is the case to be very safe. Because most silicon carbide MOSFETs, due to their properties, have thresholds in the region from 2 to 3 to 4 volts, and threshold generally comes down, well, it does come down over temperature, taking the gate drive negative ensures clamping that device firmly off. However, let's look at the circuits you're going to use. If you have a typical asynchronous circuit, like an asynchronous buck or a boost or a flyback, something of that nature, where you have a single switch and a diode, the diode is the free wheel, then you are not going to get any spurious turn-ons or transients, and a 0 volt there can be absolutely safe. In addition as well, if you're using a half bridge and a resonant soft switch topology, again, 0 volts can be very safe. But it's always worth checking out your waveforms, looking to see if there's any spurious voltages, and then if there is, you go negative.
Okay.
So that's the condition at 0 volts. But then, there is a hard switch condition. If you take a typical PFC, Totem Pole PFC or anything of that nature, where you have a high side device and a low side device in a half bridge, then yes, then you've got to be a little bit careful. This is where driving it negative is thoroughly recommended. And why? Really because of shoot through. Silicon carbide has very high dV by dTs and high current transitions. Those switching edges are very rapid, which is of course why you're using it, to get lower switching loss. But that can cause problems. It can cause shoot through. When that high side device is moving up and down, it can cause spurious voltages through the capacitances and currents. And this, combined with the internal RG of the low side switch, can cause a small gate spike when you don't want it. The last thing you want is the high side to be turned on and then the low side to be spuriously triggered. You're going to end up with an awful big bang.
Okay, gotcha. Now, is there an effective way to reduce these voltage spikes on the gate?
Yes, there are several ways. Common sense ways, to be honest. Nothing rocket science, Kirk. Good layout, very good layout. Watch those source inductances. Watch the package source inductance, the trace source inductance. Keep the coupling nice and tight. That's common sense. You would do that with any switching circuit anyway, wouldn't you? But in reality, another way of doing it is really Miller clamping. Let's use the gate drive technology. And what you can do, you can get gate drives now on the market for silicon carbide that have what they call Miller clamps. This particular example here shows you one we've used with our friends at Analog Devices. And the left-hand plot shows shoot through occurring. it shows basically a low side gate spike of up to 3 volts. Now, if you've got a threshold of 2 volts and you've got a 3 volt spike, you may encounter some problems. What the Miller clamp does is basically clamp out that the Miller capacitance and basically the stray inductance, and it clamps down that effect. So shoot through still happens, through spike to 1 to 1.5 volts, which is well below your threshold. So you're not going to have to worry about that low side device turning on.
Okay, good. Anything else you'd like to add regarding gate drive levels, Guy?
I think just generally common sense. Watch the strengths of silicon carbide, which is the low switching loss, the high switching speeds, do cause problems. Go on our website. We have a lot in our design and tools section, and you do on your websites too, in your tech sections, about designing gate drives. We show examples with people's different gate drives. We show changing RGs. We show practical ways to use gate drives to really optimize your system with our silicon carbide.
Great. Thank you. Yeah, that's great. Thank you very much, Guy. We appreciate your time today, and thank you all for watching our Tech Chat video. You can learn more about this and other topics on the Richardson RFPD GaN and SiC Tech Hub. Follow our Ask an Expert link to submit questions relative to design challenges you may have. Thank you.
Thanks, Kurt.